All right, so before we go across to the lab, okay, we need to fill in our predictions chart. So you guys need to be right here on this chart in your lab report, okay? You can type in the stuff to make the subscripts, okay? Just type in the numbers for now, and then just highlight those numbers, and if you go up to Format, okay, you can make them subscript after the fact in the Format menu. Okay, so just highlight the ones that you need to shrink, okay? Highlight them, hit subscript, and they'll get smaller. Right? For me, it's easier if I do it this way. Okay, predicting our products. All right, we didn't get a chance to talk about this as much as the other two classes because that's what they did today. Okay, but we'll go over it here. What kind of reaction starts out with two ionic compounds? A double replacement reaction. Okay, what needs to happen for me to predict my products in a double replacement reaction? What do I need to switch? Switch the metals. Now that's a little tricky here because this is NH4, which is a polyatomic ion, but it has a positive charge, which means it behaves like a metal. All right, so NH4 is the metal in ammonium chloride, and sodium is the metal, obviously, in sodium hydroxide. So when I'm predicting my products, if this is a double replacement reaction, I'm going to swap those two things. And so who's sodium going to end up with on this side? Chlorine. Okay, who's ammonium going to end up with? With hydroxide. All right, so I've created two new ionic compounds. What should I check about them? I should check the charges. In other words, I should make sure that they are swapped and dropped correctly. Okay, so hydroxide's a -1 and NH4 is a +1. So they're 1 to 1, they're good, and I don't need any brackets because I don't need any other numbers. And chlorine's a -1, sodium's a +1, so sodium chloride is also fine the way I have it written. Okay, and then I would balance the reaction. Everything's a 1, so I'm good. All right, everybody follow there. Okay, just because we're predicting these reactions, does that mean that this is exactly the way the reactions are going to go? It's not, and that's fine. Okay. What we'll look at is when we get our observations done, what went wrong? Okay, what did we do? What didn't work out the way we predicted? And then figure out why. Okay, all right, for pair number 2, I've got CH3COOH. This stuff is acetic acid. In other words, it's vinegar. Okay, and it's reacting with sodium hydrogen carbonate, baking soda. All right, now this one's a little trickier. Is it still a double replacement reaction? It is, but it's masked. Okay, because this compound here doesn't look like an ionic compound the way it's written. It doesn't start with a metal. Okay, what we really have here is CH3COO, which has a -1 charge. It's acetate. It's in your table of polyatomic ions. It is bonded to hydrogen, which has a +1 charge. So this is an acid. It has hydrogen behaving as a metal. It's just not written that way. Okay, and I'm not going to apologize for that because I didn't decide that they should write that particular compound differently than every other acid, which makes no sense whatsoever. But okay, that's the way they write it. Okay, this one is written like an ionic compound, metal first, and hydrogen carbonate is a negatively charged polyatomic ion. So when this reaction happens, ideally this should be a double replacement reaction. So hydrogen and sodium are going to what? Really? Hydrogen's behaving as a metal here. Is it going to bond with the metal? This should be a double replacement reaction. So the negatively charged things like this and this need to swap partners. So who is acetate going to end up with? Sodium. Okay, so we're going to have sodium acetate, that is NaCH3COO, written the right way for an ionic compound. Okay. Incidentally, you deal with it. If you like salt and vinegar chips, you've eaten that stuff. That's the salt they put on salt and vinegar chips to make them taste like vinegar. Obviously, you can't pour vinegar on potato chips and put them in a bag for months because they'll just get soggy. Okay. This stuff tastes like vinegar when you put it on chips. Okay. And then the other compound we're going to have, hydrogen is going to go with hydrogen carbonate. So we're going to have HCO3, but we actually write it H2. CO3 rather than HHCO3, which just looks weird. Okay, from your experience mixing vinegar and baking soda together, what usually gets produced in that reaction? What happens when you mix the two together? It bubbles and fizzes like crazy. What does that mean is being produced? A gas. Are there any gases written there? There's 2 ionic compounds, which are crystalline solids at room temperature. Probably that's not right. That's okay. We're just predicting it according to the rules that we know. Okay, sodium hydroxide and magnesium chloride. Is this another double replacement reaction? Okay, so we got 2 ionic compounds. Who does magnesium end up with over here? With hydroxide. Okay, and sodium is going to end up with chlorine. All right, that's a -1, that's a +1, so that's swapped and dropped okay. This is a -1 and this is a +2, so that one will need brackets and a 2, okay, in order to be correct. We don't have to predict pair 4 or pair 5. I did not balance these reactions, by the way, guys. You'll need to go back and have a look at that. Okay. Pair number 6. I got potassium iodide reacting with lead 2 nitrates. Are those both ionic compounds? Are they metal, non-metal, or metal polyatomic ion? Gonna need a response out of somebody. Are we looking at a double replacement reaction here? Yes, they're both ionic compounds. That's the only kind of reaction that starts with 2 ionic compounds, is double replacement. Okay. So, who is potassium going to end up with on the other side? With nitrate. Okay, we got to swap the metals. All right, so potassium ends up with nitrate, and lead ends up with iodine. Now, in this compound here, lead had a 2+ charge, so it has a 2+ charge over here as well. That means we're looking at PbI2, and this compound here is already swapped and dropped because they're both 1s. Right? So we've got that one predicted. You'll need to do some balancing on that one. Okay, pair 7. I have an element in zinc, which is a metal, reacting with an ionic compound. What kind of reaction is that? It is a single replacement reaction. So, on the other side, where is hydrogen going to be? First and by itself. Good. Okay, this is a single replacement reaction. The metals, since zinc is a metal, it's got to swap out the metal that's in the ionic compound. All right, so that means that hydrogen will end up by itself, and zinc will end up with chlorine. Zinc has a 2+ charge, chlorine's a -1, so we got ZnCl2. Is hydrogen special when it's by itself? Yes, it is. So it's H2. Okay, so we have our predictions done. Are they all going to be right? Who knows? Okay, are they all balanced? No, you have to look at that part of it. Everybody with me there? Okay. When we go across to the lab very quietly through the hallway to the biology lab, we are, first off, going to get what? Safety goggles. They aren't the nice ones like we have in the chem lab. They're the old-fashioned kind that are ugly and uncomfortable, and you will wear them anyway. Okay? And they will stay over your eyes at all times. If you want a lab coat, there are lab coats in there, but that's the biology lab. They're covered in gore. Okay? That's pieces of like the dissected things that they dissect in there. All right? It also smells funny in the biology lab because the formaldehyde they keep everything in smells bad. Okay? So just be aware. It's a different lab situation than you're used to. Okay? All the materials I will put on the front desk. One member of your group comes up to get them, then follow the instructions on the procedure. This lab should take a lot less time than the first one because we have a lot less to do. All you got to do is mix 7 pairs of things. Okay? You don't have to do 4 tests on a dozen different compounds. You just need to mix some things together and record what happens. Okay? One of the things that is going to be strange, okay? One of your materials is phenolphthalein. That's this C20H14O4 stuff. It's what they use in CSI to detect the presence of blood. Okay, like they take the cotton swabs, they rub something, and then they put this clear stuff on. It turns pink on the swab. If you've ever seen that, okay, that's phenolphthalein. Okay, it's an indicator. It will be in a squeeze bottle. Okay, there will be several squeeze bottles up there. Just take one to your desk when you need it, and You may want to write this somewhere that you're taking with you across to the lab. You only need 3 drops. How many drops of phenolphthalein do we need? Okay, 3 drops. Don't put any more than that in. It's just wasting it. 3 drops is lots. Okay? Now, the other thing you need to be aware of, because lots of times people don't read the procedure carefully, okay? When you're done pair 4, do not take it over to the waste bucket. You need the product of pair 4 as one of your reactants in pair 5. Okay, so have pair 4 go on, record whatever happens, and then keep it and go get substance C and add it to it. Does everyone follow? Now, you have a clear watch glass. It's transparent. The tabletops are black. It would probably be a good idea to have a spare sheet of paper around to have underneath the watch glass. Okay, for 2 reasons. Any dark color changes are not as clear when you're on the black background. Any light color changes are not clear on a light background. So make sure you look at the before and after over both a black and a white surface so that you can see any differences. I'm telling you that because one of your precipitates that you're going to get is white. And if you have it over the paper, you won't see it. Okay? One of your color changes is to a deep purplish red, and if you have it over the black surface, you might not see it. Okay, so just be aware you need to have 2 colors, black and white, okay, in order to see all of the color changes. Some of them, it won't matter where you have it. You're going to see them and they're bright and obvious. Okay, but there are 2. Okay, questions before we go across? Okay, quiet like mice. I'll lead you across, please. Now, when we were across there in the lab, okay, we got to discuss a couple of the observations. First off, in pair 1, where we mixed sodium hydroxide and ammonium chloride, what was our most important observation there? What happened in that one? It had a really strong smell, which means what did it produce? It made a gas. That's not how we predicted it, though. Okay, we predicted this as a double replacement reaction. It is a double replacement reaction, but it's not a strict double replacement reaction. So the big hint I'm going to give you for your analysis, don't change your prediction. Okay, it's fine. The predictions doesn't matter if they're right or wrong. Okay, but in your analysis, when you're writing out this particular reaction, the gas that was produced was ammonia, NH3, okay, or nitrogen trihydride. That's the stuff that's in Windex. It probably smelled a little bit like Windex when you did that reaction. All right? So that was one of the products. The rest of this reaction goes pretty much the same as a normal double replacement reaction. What you guys need to figure out is, where did this NH3 come from? And what's left there now? Okay? If I take an N and 3 H's out of that compound, what's left? Okay? And then, how would the double replacement reaction that occurred look after that? Okay? You guys need to figure that part out as your analysis. That's a pretty big, juicy hint for that one, though. Okay? Pair 2, same problem. We mixed vinegar and baking soda together, and it bubbled and fizzed. Okay? We did not predict a gas being formed with this set of compounds. So obviously, that set of compounds may not be entirely correct. What gas gets formed when you mix vinegar and baking soda? Anybody know? The gas that gets formed is carbon dioxide. Okay? Your products are carbon dioxide and 2 other compounds, which are both ionic. So much like pair number 1, once the gas is formed, whatever is left is behaving pretty much like a normal double replacement reaction. Okay? What we need to look at is, where is the most likely place for the carbon and the 2 oxygens to have come from? I would say probably here. So if a carbon and 2 hydrogens are gone from that compound, look at what's left, and then perform a double replacement reaction prediction after that. Okay? Remember that you need to double check your other reactions as well and make sure that they went at least as you think they should have. That is how we predicted them. Remember that in the analysis, you do need to write the balanced chemical equations, kind of like this, okay, but obviously fully done and balanced, as well as the reactions in words, with the exception of 4 and 5. Okay, they're already in that chart for you, so you don't need to worry about them. Okay, everybody clear there? Then in question number 2, 2 of your reactions should have produced precipitates. What you need to do is look at the products of those reactions and figure out which of the compounds that were the products of those reactions would not be soluble using your solubility chart. Okay, so if you found, let's pair 3. Did it have a precipitate? I sure hope it did. Okay, should have had a white precipitate. What you need to do is figure out if these are the correct products, which of them is the precipitate. Okay, using your solubility chart. And you have one other reaction where that occurred, and you have to do the same thing for that one. All right, everyone understand what the expectations are? Okay, you still have about 6 or 7 minutes. Okay, you might want to talk over with your group your reactions, okay, and see if you can put more than one head together, okay, and see if you can get those reactions figured out. Okay, the lab report is due on Tuesday, so make sure you have it done before then if you want me to look it over. Okay, make sure it's submitted by then.